Hi there, welcome or welcome back to 3 Inquisitive Kids. So this is the final lesson of 8th grade math, and it is also the final lesson of chapter 13. So in this lesson, we will be finding the interior and exterior angle sums of polygons. So continuing our chapter all about geometry, we already went over the properties of parallelograms, determining parallelograms, midlines, and now we're going to get on to our final lesson, the sum of the interior and exterior angles of a polygon, which you can also say as interior and exterior angle sums. So the two learning goals for today is to explore the sum of interior and exterior angles formulas for polygons in different ways. Use the sum of interior angles and exterior angles of polygons to solve problems. So let's look at the sum of interior angles of a polygon. So the interior angle sum of a polygon. Here's our first question. What is the sum of the interior angles of a triangle? The triangle interior angle sum is always 180 degrees. So when you're being asked in a problem, what is the interior angle sum of a triangle, the answer never ever changes. For whatever shape or type of the triangle it is always 180 degrees as its interior angle sum. Question 2. Do you know the sum of the interior angles of a rectangle and a square? The rectangle interior angle sum is 360 degrees. Now, a square is basically a shorter rectangle. A square, you can think of it as a special type of a rectangle. And this question is easy to answer because you already know from the properties of rectangles that rectangles have 4 angles that are all measured 90 degrees. So when you have 4 90-degree angles multiplied together, you get 360 degrees. How can you find the interior angle sum of any polygon? That's what we're going to be focusing on today. What if I gave you a trapezoid, a quadrilateral? Or what if I gave you a pentagon, a hexagon, right? We need to be able to find the interior angle sum of any polygon. Predict and prove. The interior angle sum of quadrilateral ABCD is 360 degrees. So here is our quadrilateral ABCD, and we're going to go over this problem together. Can you explain your conclusions in terms of what you have learned before? So here is our first method that we can solve this. As shown, we can connect AC. The quadrilateral will then be divided into 2 triangles. So the interior angle sum of ABCD will be 180 degrees times 2, which is 360 degrees. So what we are doing now is just finding a way to split this quadrilateral into triangles. Depending on how many triangles there are, we can just multiply that number by 180 degrees, which gives us 360 degrees. Here's our second method. As shown, from any random point E inside BC, we can connect AE and DE. So on BC, we have a midpoint, E. So on BC, we can take any random point. Remember, it's not just how it is drawn in this figure. When you're solving mathematical word problems, especially geometry word problems, when a question says random point, remember that you are underlining random because that does not mean that that point is exactly at the location of how it is drawn in the figure, right? It's any point. So E could be here, E could be here, E could even be on B, or E could even be on C. So taking any random point, we connect that point with A and D. This splits the quadrilateral into 3 sections, which is 3 triangles. So the interior angle sum of ABCD would be 180 degrees times 3 minus the angles of AEB plus AED plus CED, which is 360 degrees. So this is the second method for us to get to the same answer, right? So even with different methods, it gets us to the same answer. Depending on who you are and how you learn better, right, different methods work better for you. But personally for me, I think method 1 is the simplest, and if I were to solve this problem, that's probably the method that we would solve. But it's really helpful to look at how different people might solve the same problem differently. There is even a third method. As shown, take any random point E from the inside of ABCD, and then we can connect it to each of the vertices. So taking any random point called E inside this quadrilateral, and we connect it with A, B, C, and D, we split the quadrilateral into 4 triangles. Splitting it into 4 triangles, the interior angle sum of quadrilateral ABCD would be 360 degrees, because we are multiplying 180 degrees by the number of triangles, which is 4. But remember, we have to minus the angles that were recounted twice. After that, we have 360 degrees. Still, I prefer the first method because in that method, you did not have to do any of this extra subtracting stuff. There's even a fourth method. As shown, take any point P from outside ABCD and connect PA, PB, PC, and PD to split it into 3 triangles. So the sum of the interior angles of the quadrilateral ABCD would be 180 degrees times 3 minus 180 degrees, which would be 360 degrees. All 4 of these methods use the idea of conversion, quadrilateral division, and transform the problem to what we already know how to do, which is finding the triangular angle sum. So what this is saying is all 4 of these methods use conversion, which is converting the problem of what is the interior angle sum of this quadrilateral into what is the interior angle sum of all of the triangles that this shape can be split up into, without counting any angles twice. And since we already know the triangular angle sum, by cutting this quadrilateral into different triangles, that helps us to turn something we don't know how to do yet into something we already do know. So here's the conclusion. The interior angle sum of quadrilaterals is 360 degrees. Here's our first example. If one set of opposite angles of a quadrilateral supplement each other, what does this mean for the other set of angles? Please explain why. As shown in ABCD, the sum of angles A and C is 180 degrees. Because angle A plus angle B plus angle C plus angle D is equal to 360 degrees, we know that angle B plus angle D is 360 degrees minus angles A and angle C, which is 180 degrees. So if one set of opposite angles of a quadrilateral is complementary, then the other set of opposite angles is complementary as well. Now let's do a step-up problem. Step-ups are usually a bit more challenging. As shown in quadrilateral ABCD, angles A and C are supplementary to each other. Remember, supplementary means added together they form 180 degrees, and also remember that complementary means when they are added together, they form 90 degrees. BE bisects angle ABC and DF bisects ADC. So if BE is parallel to DC, prove that DCF is a right triangle. Alright, so there's multiple steps to this. Here's our proving process. In quadrilateral ABCD, angles A and C supplement each other. So we know that angles ABC and angles ADC supplement each other as well. Added together, they form 180 degrees. And we know this because in a quadrilateral, remember that's what we just went over, when one set of opposite angles supplement each other, the other set must also supplement each other. Because BE bisects ABC, angle ABC, DF bisects and that DF bisects angle ADC, we know that the sum of angles CDF and EBF is 90 degrees, so they complement each other. This is using holistic thinking. Therefore, triangle DCF is a right triangle. Question 5. Can you choose a method to find the sum of the interior angles of pentagons and hexagons following the method of finding the sum of interior angles of quadrilaterals? So using the process of the thinking of what we just did on quadrilaterals, please use the same method on pentagons and hexagons. Pause the video and try to see if you can do this. The method and the way of thinking actually hasn't changed. The only thing that has changed is the number of sides has increased. For example, we always start by trying to figure out how many triangles we can split this quadrilateral into. this pentagon into. So here we have AD and AC formed by connecting vertex A with two other vertexes, C and D. Since this pentagon can be split into 3 triangles, we know that its interior angle sum would be 3 times 180 degrees, which is 540 degrees. Now we can do the same thing for the hexagon, but this time we need to include another line since it has one more side. Again, all we have to do is multiply 180 degrees by the number of triangles it is split into, which is 4. So together it is 720 degrees. Now let's look at a quick figure that helps us conclude everything that we've just learned. So we have a triangle, quadrilateral, pentagon, and hexagon, and as you can see, the pattern is that one more side keeps being added on. Now let's look at the number of diagonal lines that each shape has from the vertex of the polygon. So a triangle can form 0, right? Because it is already a triangle itself. It's already one triangle. A quadrilateral, from one vertex, you can only connect to another vertex since you're already connected by a side to 2 other vertexes. So you can only connect to your opposite one. In a pentagon, that case is 2, because when you start from any random vertex, you can only draw another line to connect to 2 more vertexes. For a hexagon, that is 3. From any single vertex, you can take 3 lines to connect to another vertex. Concluding from this pattern that we saw, if there is a polygon with an n number of sides, how many diagonal lines can it form from any vertex of that polygon? Well, as we can see, in a triangle, a polygon with 3 sides, 0 can be formed. In a quadrilateral, a shape with 4 sides, 1 can be formed. A pentagon, a polygon with 3 sides, 2 can be formed. In a hexagon with 6 sides, 3 can be formed. So what is the answer to this problem? N, whatever the number of sides that shape has, minus 3. In a triangle, how many triangles can it split into? That would be 1. Quadrilateral, that would be 2, because you can connect a diagonal right here and split it into 2. A pentagon, 3, hexagon, 4, so on. And according to this pattern, when you have a polygon with n sides, the number of triangles that you can get split into would be n minus 2 triangles. So here is the interior angle sum. 1 times 180 degrees, which is 180 degrees. 2 times 180 degrees, which is 360 degrees. So all we're doing is taking the number of triangles that it can split into and multiply that by 180 degrees. As you can see, the pattern goes on. If this was to apply to a polygon with n sides, then the answer for this would be n minus 2 times 180 degrees. Now this page is very, very important because it's basically a graphic summary of everything we have talked about so far. So I highly recommend you to pause the video and quickly jot this down. Alright, moving on to our next slide. Here's a conclusion from this. We can start with a polygon, but using conversion and cutting it, we can cut it into multiple triangles. And as we split, we have to keep in mind the positional relationship between the segmentation point and the polygon. So here there are 4 very important vocabulary words that we went over. Vertex, a point on a polygon, a side, which is obviously one of the straight lines that form the outer edge of a polygon, the interior, which is on the inside, and exterior, which is on the outside. The interior angle sum of a polygon with n sides would be n minus 2 times 180 degrees. Really, the main thing that we've learned from this lesson is this formula. Now let's do a problem. The sum of the interior angles of a polygon is 720 degrees more than the sum of the interior angles of a quadrilateral, and all the interior angles of this polygon are equal. So how many degrees is each interior angle of this polygon? Now pause the video and use the formula we just learned to help you solve this problem. Okay, so this has included a little bit of algebra. Even though it is a geometric problem, here we do have to set variables. Let this polygon have n sides. So from this information given in the problem, we can write the equation n minus 2 times 180 degrees times 180, which is the formula we learned, is equal to 360 plus 720. Solved, n is equal to 8. So because this is a regular polygon, we know that each angle measures 135 degrees. So basically all we did was first find out, right, because in order to find out the interior angle sum of this polygon, we first had to figure out how many sides this polygon has. So we first set a variable, solve for that variable, and then apply this variable into our formula, right? So that gives us 135 degrees. Example 3. As shown in pentagon ABCDE, angle C is equal to 100 degrees, angle D is equal to 75 degrees, angle E is equal to 135 degrees. AP bisects angle EAB. BP bisects angle ABC. So find the measure of angle P. Okay. So here we have to apply holistic thinking, which is thinking of a group of objects as a whole. The interior angle sum of a pentagon is 540 degrees. That's something we already figured out from the table. And if you haven't figured that out yet, or if you haven't memorized it, which you actually don't need to, all you have to do is quickly use that formula and find the interior angle sum of a pentagon. The measures of angles C, D, and E can be used to find the measure of the sum of angles EAB plus ABC. Then, according to the definition of the angle bisector, we can find the angle sum of angle PAB and angle PBA, as well as the measure of angle P. So that was our analysis. What is our actual solution? Well, all we do is follow the steps that we mentioned in the analysis. Because angles EAB plus angle ABC plus angle C plus angle D plus angle E is equal to 540 degrees, which is the interior angle sum of this pentagon, angle C is equal to 100 degrees, angle D is equal to 75 degrees, and angle E is equal to 135 degrees. So from that, we know that the sum of angles EAB and ABC is 230 degrees. And since AP bisects angle EAB, we know that angle PAB is 1/2 of angle EAB. So with the same reason, angle ABP is 1/2 of angle ABC. Because the interior angle sum of this small triangle here is 180 degrees, we know that angle P must be 180 degrees, taking away the two other angles in this small triangle. Therefore, angle P is equal to 65 degrees. Now we're going to look at the exterior angle sum of polygons. What is the total measure of the angles that Combin turns his body every time he runs a lap? So here we can definitely see that this park or this path forms a pentagon, right? So there is A, B, C, D, and E as its vertices, and there are angles marked 1, 2, 3, 4, and 5. But as you can realize or see, these numbers, these angles are not marked inside the pentagon, but outside the pentagon. So what does that mean? So here's the concept we're going for. The angle formed by one side of the interior angle of a polygon and the opposite extension of the other side is called the exterior angle of the polygon. As shown, the exterior angle of angle A is angle 1. So what this is saying here is this is the pentagon we are looking at, and the exterior angle of angle A, which is this angle right here, that is an interior angle. When you extend AE like this would be its exterior angle. So you guys first have to understand what is the definition of an exterior angle. The sum of all the exterior angles of a polygon is called the exterior angle sum of the polygon. Just like we have interior angle sum, we also have exterior angle sum. So essentially what we are doing is just extending, right, each of these sides to form an exterior angle for each of these interior angles. What is the relationship between an exterior angle and its adjacent interior angle? Well, our answer is that they are supplementary, because let's take an example. This is angle A, that is an interior angle. Its corresponding exterior angle would be angle 1. And since they fall on the same straight line, it means that added together they must be 180 degrees. And here's our second question. What is the sum of the 5 exterior angles plus their respective adjacent 5 interior angles? So what is the sum of all 10 of these angles, both interior and exterior angles? Well, we will have 5 times 180 degrees because each pair of interior and exterior angles is 180 degrees. 5 of them will make 900 degrees. Question 3. What is the relationship between the sum of the 5 flat angles and the sum of the interior and exterior angles of the pentagon? The exterior angle sum of the pentagon is 5 flat angles, which is the pentagon's interior angle sum. 5 times 180 degrees would be 360 degrees. So our conclusion is that the exterior angle sum of pentagons is 360 degrees. Take an exterior angle at each vertex of the polygon with n sides, and the sum of these exterior angles is called the sum of the exterior angles of the shape. Think, what is the exterior angle sum of a polygon with n sides? Well, we can make a table and we can create our own formula, just like we did with the interior angle sum of polygons. Exterior angle sum of an n-agon, which is a polygon with n sides, will be n flat angles minus the interior angle sum, which is equal to 360 degrees. So the exterior angle sum of the polygon with n sides is 360 degrees, and it will always stay the same. So this is not affected by how many sides this shape has. Whatever the number of sides this shape has, its exterior angle sum is always going to be 360 degrees. Question 4. Recalling the properties of regular polygons, what is the measure of each interior angle of a regular polygon? What about exterior angles? Each interior angle has a measure of n minus 2 times 180 degrees over n. So each exterior angle has a measure of 360 degrees over n. Pause the video and read these questions and fill in the blanks. Alright, so what were your answers? Your two answers should have both been hexagon. If the interior angle sum of a regular polygon is 120 degrees, then this shape is a hexagon. Again, we used the same formula we had for interior angles that we covered earlier that you took notes of to show that this shape has 6 sides, which means that it is a hexagon. Given that each exterior angle of a polygon is 45 degrees, the polygon is a hexagon. So what we're doing now is using our exterior angle sum formula to get us 6 sides that this polygon has, which is 45 degrees, which makes each exterior angle of a polygon 45 degrees. Practice. Complete the table. So here we have a table. On the left side we have the number of sides, and on the right side we have interior angle. So all we're asking for in this interior angle column is how much does each interior angle measure, assuming that this shape is a regular polygon. Assuming that it is a regular polygon, for a triangle, which is a polygon with 3 sides, each angle would be 60 degrees. You may have learned about the properties of equilateral triangles before, and you may have learned that every single equilateral triangle will always have an interior angle of 60 degrees. And now if you are a quadrilateral and you are a right quadrilateral, which makes you a rectangle, each angle is 90 degrees. If you are a regular pentagon, each interior angle will measure 108 degrees, so on 120 degrees, 135 degrees. Now when we get to a polygon with n sides, using the pattern that we got from the previous sets of numbers, we know that n minus 2 times 180 degrees, which is the total interior angle sum, minus the number of sides and angles there are, which is n. Let's do a fourth example. Given a polygon whose interior angle sum is 2 times its exterior angle sum, find what this polygon is. Again, we need to apply the formulas for either interior or exterior angle sum to solve this problem. Let's assume that this shape has n sides. Since its interior angle sum is n minus 2 times 180 degrees, and its exterior angle sum is always going to be 360 degrees, we know that its interior angle sum, which is now replaced with its formula, is equal to 360 degrees times 2, because it says in the problem 2 times. Now all we have to do is solve for n, which is 6. So now we can answer the problem by saying this shape is a hexagon, because now that we know its number of sides, we can just call it by the name of a polygon with 6 sides, a hexagon. Given that the ratio of a polygon's interior angle sum to its exterior angle sum is 7 to 2, find the number of sides on this shape. There's multiple ways to do this, but here is our first method. Assume that this shape's interior angle sum is 7x degrees and its exterior angle sum is 2x degrees. We can make the equation 7x plus 2x is equal to 180, and this is a very favorite method of mine when it comes to having to apply algebra in a word problem that has ratios. All I do is choose the same variable, and then I do 7x to 2x. Or if the ratio is 3 to 7, or let's say 3 to 10, I do 3x to 10x, or 3a to 10a. So what I do is always choose the same variable times the number of units in that ratio. So after solving this equation, x is equal to 20. Therefore, each interior angle of this polygon is 140 degrees, and each exterior angle is 40 degrees. 360 degrees minus 40 degrees is equal to 9. So this is a nonagon. And a nonagon, just for review, is a polygon with 9 sides. But are there other solutions? As I said, there is a method too as well. Assuming that this shape has n sides, we can make the equation 180 times n minus 2 over 360 degrees is equal to 7 to 2. So what we're doing here is taking the ratio but putting it in fraction form, and then having an equal sign in between them to show that these are equivalent ratios. Solved, n is equal to 9. So this is a nonagon, especially when you are trying to find a variable. Again, algebra, but there are ratios. I like to turn them into fraction form so they're easier to compute. And then if they are equivalent or if they have any relationship between them, I like to write that relationship down and then put the equivalent sign in between. And that makes it an easy equation for us to use algebra to solve. Here is a step-up problem, a slightly harder problem. An exterior angle of a regular polygon is 60 degrees greater than an interior angle. Find the measure of each interior angle and the number of sides of the polygon. Now I want you to pause the video and just try your best to see if you can solve this problem. You don't have to get the right answer, you don't even have to get an answer, but I hope you try as much methods as you can. Alright, so here is our solution. Let each interior angle measure x degrees and each exterior angle measure y degrees. Then we can create a system of equations out of the formulas and including the information that we are given, relationships that we're given in this step-up problem to write a system of equations. Solved, x is equal to 60 and y is equal to 120. And now since the exterior angle sum of any polygon is always 360 degrees, we know that this polygon has a total of 3 sides, meaning that each interior angle of this polygon measures 60 degrees and that there are 3 sides on this polygon. Example 6. As shown in the figure, in the regular pentagon ABCDE, we can connect BE and then find the measure of angle BED. So from what is given, we can again create this equation, and then from this equation we can solve to get 108 degrees. Since AB is equal to AE, we know that angle AEB will measure 36 degrees. So the angle's measure of angle BED will be 72 degrees. So here's our class summary. The interior angle sums of polygons. we have the interior angle sum formula and exterior angle sum formula, which is the exterior angle sum of polygons is always 360 degrees, and this is not changed by the number of sides. Regular polygons. Well, especially for regular polygons, you first have to check if these are regular. If they are not regular, then you cannot apply these formulas. So here's the interior angle formula, sum formula, and here is the exterior angle sum formula. Again, today we explore the sum of interior and exterior angles formulas for polygons in different ways. We also use the sum of interior angles and exterior angles of polygons to solve problems. Now that is the last lesson of 8th grade math course. We look forward to seeing you again with whatever videos we will publish next and we will upload next. There is always more math content waiting for you, and thank you so much for watching through Inquisitive Kids. If you found this video helpful or you liked it, please make sure to like and subscribe for more content like this. Thank you so much for watching through Inquisitive Kids, and we'll see you next time.